everyone. Today I'm going to show you 3 different ways that we can model a translating system. So this is the translating system that we are going to be modeling today. We have 2 different blocks here with labeled x1 and x2. These are being pulled to the right by the force F of t with the dampeners K1, K2, F of V1, F of V2, F of V3, as well as that they're being dampened by the masses themselves. The mass of the first one is 1 kilogram, the mass of the second one is 2 kilograms. The system of equations that can be developed from that example are seen here. In the time domain, we have the mass multiplied by x double dot, K1 and K2 multiplied by the x values, B1 and B2 multiplied by x dots. So these are also gotten from x1 is always the start for the first equation because we are looking at it from x1's perspective. For the second equation, we are looking at it from x2's perspective. So we have x2 double dot with m2, b2 and b3 multiplied by x dot, and then k2 multiplied by the x alone. These equations can be rewritten in forms of x double dot for both of them. So the first equation shows x2, where the second one shows in the perspective of x1. The top set of equations can be simplified into the frequency domain, where instead of looking at it in terms of a derivative, you look at it in terms of s values. So once again, it's from the perspective, the top one is from the perspective of x1, but instead of x dots, we have s's in place. The second one is in perspective of x2, once again with the s's in place of x dots. The final equation on the bottom is with all the values plugged into the equation and simplified down into x1 over f of s. And so that equals 3s plus 5 over 4s, or 2s to the 4th, plus 17s cubed plus 44s squared plus 45s plus 20. So the values from that last equation can be plugged directly into MATLAB itself as a numerator and a denominator, and can be told, and we can tell MATLAB to plot it as a step function, or as a step response, I should say. The graph for that step response is seen here on the right. We can also use Simulink from MATLAB to do a very similar thing, but we no longer then would have to transform the function into the frequency domain, but it requires a lot more work because the system itself is a lot larger. So here you can see that we have our step input into summing junctions as well as integrators. These all plug back into either x2 summing junction or x1 summing junction. x1 has a summing junction as well as 2 integrators, but x1 outputs to a scope, where x2 does not have an output, it just goes into itself and x1. The output of this function is also seen on the right with this graph, and if you will notice, it is the exact same graph. The same thing can also be done in the frequency domain with Simulink. This is also a lot simpler than the previous one in the time domain. So in Simulink, we can have a step function, plot the numerator and the denominator, and hook that up to a scope, and we get the same function, or the same graph out of it. So these are the outputs all that can all be seen together. As you can see, they are all the same graph, and 3 different ways to show the exact same material. So as a review, I have shown you now 3 different ways that you can model a translating function. You can plot it directly into MATLAB from the frequency domain. You can use Simulink in the frequency domain to directly plot it. And you can also then use the time domain and output that into a much larger Simulink file, but then you don't have to transform the function. Thank you for listening.